chapter 4, section 4.5. So we are looking at the superposition principle, the method of undetermined question. So this is the theorem 3 in the book. So it says that if we have this situation, we have this equation and this. So if the left side is the same, but on the right side we have two different functions, and actually k1 and k2 are some numbers, and y1 and y2 are some particular solutions of the equation 1 and equation 2 respectively, then the linear combination with k1 and k2 of these two functions will be the solution for an equation like this, like number 3. For example, it says determine the form of a particular solution to the given differential equation and do not solve. Okay? So we can think of the right hand side as like sine t as like one is the right side of one of the equation, and then cosine of 2t as right side of a second equation with the same left side. Then the homogeneous equation will give us these as the roots of the auxiliary equation. So we can say y1 is e to the negative 2t and y2 is e to the negative 3t. Now if you note on the right side of this equation, we don't have any exponential function. We have sine and cosine function, but different sine and different cosine. So when we write our the particular solution, it will be just the a sine t plus b cosine t plus c cosine 2t plus d sine 2t, because there are different sines and cosine. But then we also have to know for the general solution it will be, because it will be yh plus yp. So what is yh? Yh will be c1 e to the it will be c1 e to the negative 2t plus c2 e to the negative 3t, and then plus this whole yp, a sine t plus b cosine t plus c sine 2t plus d cosine 2t. That will be the general solution. Next is the theorem 4, which is existence and uniqueness in the non-homogeneous case. So we are saying that for any real numbers a, b, c, t sub 0, y sub 0 and y sub 1, suppose yp is a particular solution to the equation 3 in an interval I containing t0 and y1, and that y1 and y2 are linearly independent solutions of the associated homogeneous equation in the interval I, then there exists a unique solution in I to the initial value problem. So for the initial value problem we can have a unique solution, and it's given by the equation. You can check in the book what the equation is. Basically it is saying that will be the y will be equal to yp plus yh, and where yh is c1 y1 plus c2 y2. So example, find a particular solution to first this equation and then second this part is this. Now if you look at the right hand side, there are two of these functions added, and actually we have done these examples in section 4.4, when one example we did was how find the like a particular solution to this one, and then find a particular solution to that one, and we found the particular solutions which came out to be these. So now by the superposition principle, because now we see these two functions being added, just the same function. So what we will do, our yp now will be just the sum of those two functions. So why am I getting a negative? Okay, so I have the first one and the second one. Okay, so second example, because now b part, now it is negative 9t plus 20t. So if you notice, negative 9t is actually negative 3 times 3t. So the particular solution for 3t we know, so we multiply that by negative 3. So this is your k1. K1 is negative 3. And then if you notice the 20 e to the t3 is 2 times 10 e to the 3t. Now for that we know the particular solution, and this is k2. So when we write our solution, it will be negative 3 times the yp for that part plus 2 times the yp for the part associated part. So we will just multiply by negative 3, distribute, and 2 over here. So we end up getting that as a particular solution for this part B. Now example 3, a particular solution to the differential equation. This is given to be tangent x. Give the general solution of the equation. So what we do, we first find the auxiliary equation, find the corresponding functions of the auxiliary equation. Now note here, the function is given in terms of x. So we will have y1 is equal to e to the minus square root of 2x, not t. In the same way, y2 will be e to the square root of 2x. So that yh becomes c1, remember c1 y1 plus c2 y2, so we get our yh in this form. So now general solution will be just add the yp and the yh. So here, this is the general solution. So example 4, it says, determine whether the method of undetermined coefficients together with superposition principle can be applied to find a particular solution for the DE below. Do not solve. So in this case, if you look at the right hand side, you might say, oh, but this is sine cube t and this is cosine hyperbolic t. I don't know if you have had hyperbolic functions before or not, but they are something like the simple trig functions are defined on a circle. So the hyperbolic functions are defined on a hyperbola. So anyhow, so actually the sine cube t, if you recall, somewhere in trigonometry you learn how to convert the sine 3t, simplify and write it as powers of sine, sorry, not power, so as powers of sine of t, theta. So if you have sine of 3 theta, we can convert it as powers of sine of theta. So using that identity, we can actually find out what will be sine cube theta, and that is what I have written here. So you see, we have now converted it into, we had a power, now we have now the first power, but the angles are different. So this is something that we can easily find the solution. Okay, or we can easily write our particular solution for. Now cosine hyperbolic has this definition that it is equal to e to the x plus e to the negative x over 2, so which gives us some functions whose from which we can easily write our particular solution. So it means we can convert the right hand side into functions whose particular solution we can easily check or find, and then so yes, this will be doable. Okay, I think this is the two more examples. Okay, again, find the general solution to the differential equation. So we will again finding the left the solutions for homogeneous equation y1 and y2, and we see that these are exponential, and the right hand side is going to be sine and cosine, so they don't overlap. So we simply write our take our yp as a sine theta plus b cosine theta, because these are the same angles here. So and then take the derivative, plug into the equation, compare coefficients, and we get our particular solution. So we can then write the general solution like this. So note here, in this case, the r, one of the r value was 0, so this gives me e to the 0 theta, which is just equal to 1. Okay, now last example here. So this is an IVP, so it's actually a long example because the question asks us to find the solution of the IVP. So first we find the particular solution. We note that the homogeneous equations give us the exponential functions, and in the right hand side we also have exponential functions, but they are different from the exponentials of the homogeneous case, so they don't overlap, so we are fine, just keep doing the work. So yp comes out to be this. Now we write the general solution to find the C1 and C2, take the derivative, plug in the initial conditions, simplify, and we end up getting final answer down there. So it's a long question. I hope you won't get this long a question in the exam, but you should know the procedure. So maybe if this much is solved and you are asked to go forward from there, so you should know how to do that. So this is all you need to know from section 4.5.